So it is my distinct pleasure to welcome our visitor today, Guilherme Franzmann, who is visiting in the context of our FNS project that we have about the philosophy beyond standard physics. He is originally from Brazil, where in Florianopolis. He did his undergraduate degree in physics and then in Sao Paulo, a master's degree in theoretical physics. He then moved to Canada to do a PhD at McGill, I think, right, with Robert Brandenberger in cosmology. And he is now assistant professor at Nordita Institute for Theoretical Physics in Stockholm, and an associated or affiliated with the Department of Philosophy at the University of Stockholm. He is working on cosmology and quantum gravity primarily, and is very, very interested in the philosophical foundations of these fields, which is why he has a long history of having interacted with us philosophers. We're very happy to have you here. Looking forward to your talk, which will be on subsystems and quantum mechanics, QT, and beyond. Please.
Thank you. Thanks so much for the introduction. Thanks for the invitation. I'm very happy to be here. So this is actually the first time I'm giving a talk, an invited talk to a philosophy group. I've done that in Stockholm before, but I never went away from my home institution to talk to philosophers in particular. So it's quite a privilege for me to be here. I'm very thankful for the invitation. Now, despite me being somehow associated with the philosophy department at Stockholm University, by no means I want you to think of myself as a philosopher. And I say that out of insecurity, right? So this is kind of like a physics talk adapted to the best I could to a philosophy community or philosophers watching this talk. And with that, you have to pay the price that I will break protocol and I will invite you to ask questions during the talk. I know that's not the common attitude that you have. You're more than welcome to hold all your questions to the end. But if you do have some questions during the talk, I'm happy to have that discussion. There is a lot of things that I want to cover here, but we don't have to go all the way to the end. I'm more interested in the discussion. I'm more interested in the kind of questions that I myself haven't thought about so far. And maybe you guys might come from a different angle and question some of the things we're doing here. And then hopefully I can learn with that and vice versa. Okay? So before we start, a lot of this work has been done in the context of this collaboration. It's called Emergent Geometries, which Niels is also part of it. We are actually 7 different people working across different universities, coming from different backgrounds, but with this common passion of trying to somehow think of how space-time can actually emerge from some more fundamental theory. If you want to learn more about the collaboration, later on you can actually scan the QR code or check the slides. There is a website where we talk about how we're approaching this kind of conversation and what we are doing in terms of projects. In fact, this whole talk is based in our current 2 projects that we've been working on for the last year and a half or so. On the same token, we are having our first workshop in November. Since I know that you guys are working in philosophy of quantum gravity and you're interested in how space-time can emerge, we have Baptiste going to be giving a talk there. It is in November. So if you haven't applied yet, it's still 1 week left until we have the deadline. So you may actually check the website and see if this is something that you'd like to participate. It's going to be a small workshop bringing philosophers and physicists together to talk only about space-time emergence for the whole week. So you're all invited to apply. Okay, so enough of that. Let me get started. So let's get started in a very pedestrian way to get everyone on board of what is going on here. And I'm going to be very pedagogical, and I'm going to tell you a little story. And this is a story about a mysterious box. So I want you to imagine that you are this exceptional physicist or philosopher, but in this case, physicist because you're going to the lab, and you get to your lab, and you find that there is this mysterious box that wasn't there before. And then you look at this box, and you cannot make it open, but there is a display. And the display shows an energy spectrometer. And so there are some buttons, you can go there, and you can keep changing the configuration of the physical system inside of the box to different energy states. and you can actually take note of all of those. And so you do that, and you are a very curious, earnest scientist, and you want to figure out how can you model what's inside of the box without opening the box. So you go back, and you start to modeling it in the simplest possible way. You think about having spin sites inside of the box. You know how to put different spin systems together. You're familiar with the Heisenberg chain model and things like that. You know that when you have a spin site, you can do a few things with it. You can couple between different neighbors with some particular orientation of the spin and with some particular coupling constant, let's say J. But you can also put your spin site under some magnetic field. Let's call it H, in some direction, for instance, Z. So those are your Lego, like, building blocks to create a model for what's inside of the box. And then turns out that with those building blocks, you come up with a model. And your model looks like this. Somehow you have 4 different spin sites inside of the box. They have neighboring-like interactions, all with the same strength. You also somehow imagine that there is a magnetic field inside of the box affecting all the different spin sites. You write this theory down, you compute the Hamiltonian, you find the eigenvalues, the energy spectrum, and it matches precisely with all the displayed values in the box for some value of the magnetic field and some value of the coupling constant. That's very exciting. You understood whatever was inside of the box by just relying on your modeling skills, right? So what do? You go and you tell your colleagues that, wow, I mean, look at what happened. There was this box in my lab. I was able to model it. And as you're trying to tell your friend what was your model, they say, stop, 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 because I also want to have a try. I also want to try to model what's inside of the box. So now your friend goes out and they try to model inside the box. And they take a similar strategy, but it's not exactly the same of what you did. They also have some couplings between neighboring spin sites, but they have a different value for the coupling, which is actually what they call H, which turns out to be what you thought was the magnetic field inside of the box. And they also have 2 different magnetic fields inside of the box, one affecting 3 of the spin sites in one direction, and another magnetic field affecting the other direction. For this first magnetic field, they actually have the field being J, which was your coupling constant for those different spin sites. But the surprising thing is that they go on, they compute the Hamiltonian, they find the energy spectrum, and you have exactly the same energy spectrum. And that's a bit puzzling, because now you are talking to each other, and you both thought that you knew what was inside of the box, but you have very, arguably somewhat different understandings of what could be the physical system that is responsible for that physical energy spectrum that is displayed on the box. So you take some time to discuss, and then finally you realize that there's a dictionary between those 2 models, which is schematically written like this. But basically the idea is to say that what you represented as spin sites, your friend might have represented as interactions of your spin sites. And there are other kind of relationships that are a bit weird as well. I want to focus on 2 of them, which is the fact that for your friend, one of the spin sites somehow corresponds to the interaction of all your spin sites. And also you have, depending on the direction, couplings between different spin sites being responsible to a single degree of freedom in a given direction for your friend. So what is happening, right? And that's the whole point of this talk, which is, in this case, what is happening is actually quite well known. We just have a duality. So there is a way of writing the Hamiltonian in those 2 different models, which is completely different mathematical representations of whatever the system inside of the box, but with different degrees of freedom. What is surprising about this is that, as you saw, those degrees of freedom, they relate to each other in a non-local way. So what you can see as 1 degree of freedom in one theory is actually interaction of all degrees of freedom in the other theory to some extent. And now you can still be curious, like, well, what is happening? I want to know which one of those models is the one inside of the box. We're talking about what we think very physical, tangible things, like there is a magnetic field in one direction as opposed to the other direction, right? Those are things that, in general, we don't think that they are somehow dubious in whatever is happening in a physical system. Well, usually when I give this talk when I'm further north in Europe, and I tell people, well, you go south, you go to CERN, and you break things open. But actually, we are very close to CERN.
We're south, so.
But you're south, so you have to go north now. And so that's what we do in a daily basis, right? I mean, we just keep smashing things, and we try to find other degrees of freedom that can tell us that we can break the degeneracy of those different modelings that we have for a physical system. But what if you cannot open the box, right? That's going to be what this talk is about. If you cannot open the box, the analogy here basically is telling us that we seemingly have different descriptions that have different notions of what we call systems, different notions of which part of those systems are actually interacting. And to some extent, the word spin site is very suggestive. Site is a location, like I take a spin site and I put one here and one here and one here. But suddenly, if the two different models, they don't agree anymore with the notion of site, the very notion of location or spatiality within the system might not be so well defined anymore. And the question is, how do we make sense of that? So this is the introduction. Hopefully you're on board that we should talk about those things and we'd like to understand them better. But to do that, now we go back in time. We go back all the way to classical mechanics. And we're going to do a lot of the heavy lifting for this talk there. Because in classical mechanics, hopefully we're much more used to the notion of states, observables, phase space, so on and so forth. And then once we do the heavy lifting there, we do a bit more lifting in quantum mechanics, a little bit more in QFT, until we maybe talk a little bit about beyond QFT/quantum gravity. Yeah.
So in all this duality, but what is there the difference between duality and symmetry? Or
That's a very good question. And maybe I will park this question. So please ask questions, but some questions I'll just park to the end because I think those are worth discussing and would be a bit of the tour of the talk. But of course, there is a lot of talks about that and discussions about what's the difference between duality and symmetry. And in fact, in the new book by DeHaven and Butterfield, they have a whole chapter where they try to draw the line between duality and symmetry. So we can talk about that towards the end, maybe. Okay, so let's do classical mechanics, right? So classical mechanics, we start with the notion of system. Usually think about a point particle. So I have a point particle, I have a phase space, which is like the set of oppositions and momenta of this particle. And quite quickly, we generalize from one particle to the n particle state. And we draw a phase space, which has all the different positions of the particles, all the different momenta. So this is like your kind of like your stage space where things are happening in classical mechanics. And then we define observables there, which typically what we do, we define functions in phase space that spit out real numbers to us. Those are going to be the observables in classical mechanics. And typically the only condition that we start off, we should say that those functions they should be differentiable, they should be infinite functions. And those observables, those functions, they do form an algebra already at the classical level. It's just that they are a very simple algebra because they all commute with each other. So they are an abelian von Neumann algebra, if we're a bit more formal. Okay, so we have already now a notion of a system in classical mechanics. Now we have to talk about the notion of system and notion of observables. Now we need to talk about states. What are states in classical mechanics? Well, states you can think of as basically the things that are going to take your observables and give you numbers or expectation values together. In general, what really happens is that when you combine a state, let's say omega, with one observable, you can define expectation value. And the reason why we do that is because in classical mechanics, even though we repeat experiments, there is usually some errors. But in quantum mechanics, for instance, not only there could be experimental errors, but there is also no guarantee that the outcome is going to be the same. So we do talk much more about expectation values in the end. And in the context of classical mechanics, we already have the notion of different types of states. We have states which are pure. So you literally go and pick one precise point in phase space. But we also have the notion of mixed states, which can be sums or integrations over regions of phase space. And those are the analog kind of like mixed states that we have in quantum mechanics as well. The main difference from what we had before were about the variables to now this stage is that we further require that our variables, they also should be measurable functions. They should be bounded. They shouldn't give infinities all over the place. So we go from the algebra that we had before for variables that was just infinity functions, just differentiable functions, to now bounded functions defined on phase space. So we have systems, we have observables, we have state. Now we're ready to talk about subsystems. And the question is, how do we talk about subsystems in classical mechanics? Well, one of the defining features, both classical quantum QFT, perhaps quantum gravity, is that not only we want to talk about subsystems, but we want to be able to talk about them in a way that we can say or state things which are independent across different subsystems. And so really what we want to do is to be able to perhaps start from a big system and be able to factorize into smaller subsystems. But similarly, we want to be able to compose different smaller subsystems into a big system. And arguably, we could even expect those two things to be equivalent, that there's a way of navigating the cycle from going from the whole to the parts and vice versa. So naturally, we define systems, and you can expect that a subsystem is going to be, at the very least, a system. But because now we have the notion of independence, that we want to talk meaningfully about different independent subsystems, we have to really ask the question, what do we mean by independence? Which also goes back to the example of the box. How do we mean that we have different spin sites, especially when different models talk about those spin sites in a different way? So to do that, at least for the sake of the talk, we're going to be very operational. And I'm going to give you two operational notions of independence. One has to do with measurements, and one has to do with preparing the state of your system. So on measurements, probably you're familiar from quantum mechanics, typically what we expect is that if I have a subsystem A and I have a subsystem B, and they are part of this whole system of the two dice, and each of those die, they have their own algebra of observables, I'm going to say that I can make independent measurements if there is a way that I can show that the observables of each of those subsystems, they commute. And this, of course, may be what you're familiar with also from quantum mechanics. But see here that I'm not saying anything about the states themselves, only about me going to the lab and making measurements. But I can also talk about independence in the case of state preparations. So we can go back to each subsystem, and they have a set of different states available to each of them. And then I'm going to start now becoming a bit more abstract, a bit more formal. If the math is too much, just focus on one and the same, and hopefully that's going to be enough. We're going to say that we can prepare the state of each subsystem independently, meaning you have independence of state preparation, if for every state of one subsystem, say A, and any state of the other subsystem B, there is at least one state over the full system that reduces to the state of A or the state of B, once they ignore the other subsystem. More formally, once they trace out the other subsystem. That's going to be the notion of independence. Actually, this is called statistical independence. So if this is satisfied at the algebraic level, each of the two subsystems can be prepared in any state, independently of the preparation of the other system. Yeah.
So now we already take the composition for granted.
For now, yes. I'm glossing over some of the details because even in the slide before, I already did that, which was the fact that I wrote something like this. So somehow I'm already imagining that I have embedded my observables A and observables B into the full system, because otherwise I cannot even talk about multiplication of those observables. So point taken, but I'm glossing over that. Happy to come back to that later if you want. All right. And let me give you now when does this fail, for instance? You could imagine that this definition here is something very reasonable, but I can also give an example of when it fails to build more intuition. Let's imagine that I have just subsystem A, which is this die, And let's think about now the states not of the full system or subsystem A, but of the corners. So there is one corner one corner 2. Now, as you know, there is a constraint for the system that those 2 corners are connected by an edge. And so you know that this system here, I cannot think of it as having 2 independent corners because there isn't a global state for the whole die in which I can prepare the state of each corner in whatever way I want. So if this is 1 and 2 and they're always connected, I cannot have a state for corner 1, labeled 1, here, for instance. So there is not a state of the global system for which I can prepare the corner 1 and 2 in whatever way I want. So this is a failure of statistical independence. And of course, the key word here is there is a constraint. And we're going to come back to that, of course, later. Now, you could think that this is enough, but actually I want more. I don't want only this notion of independence for the state operation. I actually want independence of events. And so this goes back to probability. When we have 2 events which are independent, so event A and event B, if they're independent, probability of A happening and B happening, they just multiply. And so this is the same thing that's going to happen if I want to make a measurement of a given state on subsystem A and a measurement of a given measurement on subsystem B, and I want this measurement of those 2 things to be completely independent. Now, for that to happen, basically what we need to guarantee is that there is a product state across those 2 subsystems. So not only each subsystem has their own set of states, and not only the global system has a state that is reduced to each state A and B, but also that I can find a state over the global system that is not correlated when that happens. So basically, a state of the global system applied to an observable on each subsystem is a multiplication of a state on a smaller system with its observable and the product. And this is called statistical independence in the product sense. So just reading this here, each of the 2 subsystems can be prepared in any state independently, and all observables of one subsystem are uncorrelated from all observables of the other system. If you can do that, then you have this notion of statistical independence in the product sense, which is a particular case of, sorry, there's a typo here, of statistical independence in the more general case. So if this is true, then you know that this is going to be true. Yeah.
So, you can this statistical independence is the name of the more statistical independence is about the observable.
Yes.
And so, it's maybe this definition of statistical independence is do you need the first part? Can you provide a statistical independence? That's statistical independence.
That's statistical independence, exactly.
So it's all in.
Yes, okay. Precisely. Okay. Exactly. So you know that if this holds, it's because you have the first definition already holding. And of course, you could in principle violate this without violating the other one.
Yeah.
But if you violate the other one, you violate this one. That's going to be a point we're going to come back later when you talk about gravity. Okay, so I've been talking about dice, but we can quickly go over what is more or less happening in the classical case. So you could imagine that we start with a big system with its own Hilbert space, its set of observables in a particular state. And you could imagine that there are 2 different observables, 1 and 2. And you want to see if actually what you thought it was 1 and 2 different observables, they are not only different observables across the phase space, but they correspond to different subsystems of this big system. And the way to show that this would be the case would be, well, first try to find 2 other states of your whole phase space, omega 1 and omega 2, and then try to prove that actually this joint measurement of those 2 observables across the full system can be decomposed as a product like that. But similarly, you could actually focus on the factorization that we talked about before. You could imagine that this big system is actually coming from a product of 2 smaller subsystems, with their own phase space, their own variables, their own states. And then you want to prove that this guy here is actually the same as that guy there. Everything looks a bit the same, but it goes back to your question from before, which is, this is an observable defined on a subsystem. This is an observable defined on the global system. Of course, we can expect maybe I can embed this guy in the big system. And if that's true, or actually we're wondering if this is true, basically you have three different relationships that you can investigate and see if they hold or not. And if they do all hold, then you would have a notion that, okay, I did find a very clear notion of subsystems. Because those guys are defined on their own terms. These guys defined on the big system point of view term, and there is a way of like going in between them. Okay, so where are we at? This is like our task for today. We start with an operational notion of subsystem independence, meaning we want to be able to make measurements and state operations in an independent fashion. So we establish that should be our criteria for our task. And we want to go over classical mechanics, quantum mechanics, QFT, and beyond. And the question is, can we instantiate that at those different levels? Well, the story goes for classical mechanics that, of course, we can. And basically what we do, we have a Cartesian product. And through the Cartesian product, you can actually show those three different relationships we had in the previous slide to be true in classical mechanics. So we can talk about smaller phase spaces being composed in a Cartesian way together, and that inducing an isomorphism for the subalgebras into the bigger algebra, and also relating the small state space of the subsystems to the big state space of the big system. So once we do that, you actually can show that, yes, we have it. And of course, this is what we implicitly do when we learn classical mechanics. Of course, we don't talk about that, but that's what's happening when we put things together. Okay, so now the task is, let's go quantum, and let's see what else we need to make something like that to also hold in quantum mechanics. So quantum mechanics. Let's talk about quantum systems first. So now we already we did a lot of the heavy lifting. So now I'm gonna just start throwing things at you, and you can, based on the intuition that we grasped so far. Quantum system is gonna be associated with a Hilbert space instead of the phase space, a set state. For this talk, you can just think about the set density matrices. There are subtleties, we can talk about it. And there is a set of observables, which are gonna be self-joint operators in your Hilbert space. These observables do not form an algebra alone. If you take a self-joint operator times itself, that won't be self-joint. And that's why usually we have to extend the algebra to have the algebra with full, the whole set of bound operators defined on Hilbert space. So the triple that we had before, which was the phase space, the functions, and the states, now quantum mechanics we have the Hilbert space, density matrices, and the algebra of bound operators. And similarly, as we had before, we talked about expectation values, but now defined in terms of the Born rule. If we have a pure state, that's the Born rule that we have in quantum mechanics. If it's not a pure state, we generalize and we talk about trace of the states with operators. But you see the setup, the triple-like setup is there as well. Now we want to start to see the fact that somehow space is a bit hidden in quantum mechanics. None of what I talked about so far, I mean, there was in the quantum mechanics part, there's a Hilbert space, density matrices, bound operators. I didn't say anything about space or time. But there is a way in which tacitly space-time is already kind of making a show, or at least underline what's happening in quantum mechanics. And to describe that, let's think about our lab situation that we had before. So as you remember, this mysterious box was kind of like illustrating that if you think about quantum systems only in terms of the global Hilbert space, the global wave function, the global Hamiltonian, we weren't able to characterize fully things such as different sites, for instance. There is ambiguity there. It is puzzling, as I said before, because typically when I go to the lab, we seem to be able to place quantum systems after one another and we seem to be able to have a very clear picture of what is the composition of the Hilbert space. In the case of different qubits, for instance, it's going to be just the tensor product of each of the different qubits that I have in my lab, or the spin sites. And this is the general attitude. That's why we typically don't think about that when we first learn quantum mechanics. Actually, one of the sometimes explicit, quite often not explicit axiom of quantum mechanics is that when you want to compose quantum systems, you just put them together with a tensor product. And that's typically what we assume to be the case. But now let's see how, to some extent, space can show up already in this picture. So let's imagine we're back in our labs, and let's consider that we have some quantum mechanical system, which is divided in two parts, A and B, that have a global Hilbert space description. They can be interacting or not, it doesn't really matter. And now, just for the sake of the discussion, imagine that you have some clock on the background, on the back of the wall in your lab. You have system B, system A, with their measurement apparatus around the system for each of them. And so the reason why I have a clock in the back of my lab is to define some reference frame in which I can state with certainty that I can make measurements across each system in a space-like separated way. So from this lab point of view, I can make simultaneous measurements on each system. And what we would like to say when we have a space-time picture in the back of our minds is that we want to ensure that the statistics of the experiments I'm making each system, they're going to be somehow independent. Because in this case, we're making measurements which are simultaneous from this reference frame point of view. And so if I compute the generalized Born rule for a set of observables for one system, and I compute with the other system, I want them to be able to say, okay, they are completely independent. There is no signaling happening between those two procedures. So let's now consider, yeah?
So now you already have relativity in mind, or like, but then you also worry about how the code defines reference.
There is a lot to worry. And what I'm trying to do here is just to build the heuristics about the commutativity of observables. So I'm happy to talk more about that, but I am assuming that I have some notion of causality, which tells me that whatever I do here and whatever I do there, they should be somehow independent. And the point is to show that by only demanding that, I already impose some structure on the algebra of those observables at the level of the subsystems. Yeah. So, as I said, one way to do this is to say the following. If I make a measurement on B, for instance, the state of this whole system should be updated. And you can think about collapse, you can think in whatever way you want. Typically, you can do a projective measurement, but in a way that you want to say, whatever has happened here should affect my system here, even though the state of the whole system has changed. And it turns out that if you do that, impose that to be true for any observable that you can measure across system A, system B, then you arrive that the algebraic structure of the observables across each of those systems should be commutative. That's typically what we do in quantum mechanics. We say that the two systems are independent if my measurements somehow are, I can make the measurements in an independent fashion. And so this is one way to some extent, infer that I can relate the notion of space-time separability or causality with our quantum mechanical description at the level of the observables. In another way, you can almost think that measurement independence can be connected with the fact that things can be measured in a causal independent way. Now, the reason why I'm saying all of that, and why I brought uniquely this picture of space-time, is to justify one result, which is the fact that if you have those three different conditions, so let's go over them. You have sets of observables for different subsystems that you have control of. And you have that those observables across different subsystems, they commute, which can be justified on the grounds of space-time causality. And then you say that those different subsystems, they form a system, and their independent subalgebras together expand the algebra of this full system, A and B. If those things hold, then there is a theorem that you can show that this is the same as having a tensor product structure in your Hilbert space. So in the same way that when we had classical mechanics, and we had the phase space, and the Cartesian product allowed you to decompose your phase space into parts. If you have those algebraic properties on the observables acting on your Hilbert space, then you can justify or you can prove that the induced Hilbert space will be factorizable. You can actually break it in parts. But you took the whole effort here was like we're only paying attention to the algebraic structure, and from that we can arrive at the necessary conditions such that the overall space of the big Hilbert space system can be broken into parts. That was the reason why we were going through this sneak space-time picture, but we don't have to. If you impose this ab initio, you can prove that to be the case. Okay. Question?
Yeah. So before we did this theorem, how are the subsystem Hilbert space and the big Hilbert space related, like
So again, I am glossing over details. For instance, here again, we're making multiplication. Of course, those two observables define over the full system. Exactly. And then you have to prove that there is a way of showing that each of those, they form their subalgebras themselves, that you could think of them as having their own smaller Hilbert space. And then you go back and you show, oh, actually, those are exactly the Hilbert spaces that, when composed together, form the big Hilbert space. But very good point. So that's our recap. What's happening in quantum mechanics? We have this triple-like structure, and there are some interesting results. You can factorize the Hilbert space in two if the observables of their respective algebras commute. And this is an if and only if statement. So it goes both ways. Of course, if the Hilbert space factorizes, the algebra on each Hilbert space commutes. But what's surprising is that if you start with this, you can then recover the factorizable Hilbert space. If you have this tensor product structure, then you actually can prove that statistical independence and statistical independence in the product sense, they both follow. So what we had before for the classical case can be instantiated or implemented in the quantum case. And there's another theorem, which is this one coming from the causality, the argument that I just gave before, that if you consider measurements or the state date in one system to not affect the expectation value of the variables of the other system, this is true if and only if the observables commute. So we have those nice maps of relationships. So you could start at any of these points, and you can recover the whole typical theory of quantum mechanics that we have when you talk about different subsystems. This is the paper by Zanardi and others, 2003. This goes back to Schlieder in 68. So that's good, because now we are able to show that we can break the Hilbert space if those conditions are in place. And then we can safely fill in the second line for quantum mechanics. We can do the same kind of implementation we had for classical mechanics at the quantum level. But what about quantum field theory, right? That's when we really want to embed our quantum mechanical systems in space-time. So as a starter, yeah.
When you said that space-time didn't Geneva, statistical event kind of remark federation.
Yeah, so to some extent, yes. So statistical independence is deeply connected with this notion that you can make you have no signaling. And then, of course, this brings you here, which can bring you here. But as I said before, you don't have to think about this as coming from the fact that you have causality, space-time causality. If you're doing non-relativistic quantum mechanics, forget about space-time, and I tell you, this is a system, this is another system, they are independent. And of course, you have this construction as well. But then you don't have this construction because this is based on a space. Like what people do is by hand, typically. I give you a quantum system, I have my own. I don't do QFT, I do normal quantum mechanics. But then we say, we cannot signal to each other. So you impose this sort of by hand. But if this condition is coming from space-time causality, even though you haven't written down a quantum mechanical theory that is respecting relativity, for instance. I'm not sure if this helps with your question. Of what?
Of bedtime liquidity. Could you
Yeah, I think you can. I'm not sure if it would be able to right now, but I think
the superdeterministic, they reject the
they would reject the equivalent, yeah. Exactly. Yeah.
But what about homologality, where you don't like that independence?
Yeah.
Then you still have no relation.
Yeah.
That's a value of the process. Or what?
I need to think about it. Can we go back to this later when I'm done? Because no, but that's the kind of questions I want to be asked because I haven't thought about that. So that's very good. It would be nice to actually be able to now contrast these with the Bell-like inequalities and think of what are the assumptions there and what those assumptions, how those assumptions are violating or not those different things or how they're connected. But very good. Yeah, I'm happy to talk more about that. Okay, so QFT. Well, it turns out that as soon as you go towards now trying to fully embed quantum mechanics in space-time, those things are not valid anymore. So here we had if, only if, but this if, only if, it was valid for fine dimensional quantum systems. More generally, if you want, to what people would call type 1 Neumann algebras. But in QFT, you have what they call type 3 Neumann algebras, and you have these infinite dimensional quantum systems. And so those if and only if relationships, they do not hold anymore. And so we have to do better, have to bring more structure if we want to recover something like this to be able to complete our table. And so this brings us to now algebraic QFT, which is really the idea of having local quantum physics. How can we do proper quantum mechanics in space-time? So to do that, I'm going to briefly review the elements that we need in case you're not familiar with it. So when we're talking about local quantum physics, basically what we want systems to be located or to correspond to space-time regions. So we have our manifold, I have some open set in our manifold, and I want to somehow think about whatever is happening in that particular space-time region to be a system. So what we can do, we can assign a Hilbert space to the whole space-time. So I have space-time, I assign to it a Hilbert space. Somehow in my mind, if this is a manifold, the Hilbert space is a circle. I'm not sure if people ever draw a geometrical picture of a Hilbert space. So you can do that. Once you have a Hilbert space, then you have a space of the bound operators in a Hilbert space. And what you can do is to think that your space-time region, U, somehow has a corresponding subalgebra as a subset of all the different possible operators of the operators acting on the whole space-time. So that's cool, but what we cannot do is think that there is a smaller Hilbert space of the full thing associated with the region. The starting point, which has to do also with this recap that we did for quantum mechanics, that we cross all those different if and only if relationships. What's available to us initially is this algebraic framework, and then you can try out of it recover some kind of like Hilbert space factorization scheme as we had before. And that's what we're going to try to do moving forward. So to do that, we usually impose some structure for the structure in our assignment of algebras. So if you have a region U inside some bigger space-time region U prime, then you say that the algebra associated with the region U is going to be a subset of the algebra associated with the region U prime. Notice here that even though there's a subset, this can actually be an equality, because you can think of the bigger space-time region to be just the causal cone or causal diamond of a smaller space-time region. And then the algebras are the same. Then we have some notion of Einstein separability. So back to our discussion about space-time playing a role in quantum mechanics. You don't want to be able to signal between measurements that you do at space-like separated regions. So you say that the algebra associated with the region U and the algebra associated with the region V, which are space-like separated, they should commute. This is, of course, similar to the standard notion that we have from QFT of microcausality, that you have field operators at space-like separated regions commuting. So this is kind of like familiar. I guess it's not surprising. Now, really the thing here that makes all the difference, but is also quite abstract and perhaps hard to grasp, is that you need to require something called funnel property. And actually, this is something that you can prove for a variety of QFTs. So the free scalar field, free NMUs, free spinors, you can actually show this to be true. So let's unpack this. So the funnel property says the following. Take our region U, okay? Now consider this region U to be reasonably inside the region U prime. So those are open sets, but you want to imagine that there is a bit of a wiggle room between those two regions, and that can be defined in a mathematical proper way. If the funnel property is true, then what happens is that the algebra associated with the region U and the algebra associated with the region U prime has in between another algebra, which we call N. And this N is a very powerful algebra because it is isomorphic to an algebra defined on a given Hilbert space. And so this is another way of saying that, if you're familiar with the technical terms. This would be a type 1 von Neumann algebra, even though those two algebras are type 3 von Neumann algebras. And so in more physical terms, it means that in between those two different space-time regions, there is an algebra that regularizes all the things you'd like to compute in this algebra, but you can't, such as entanglement entropy, energy densities, so on and so forth. Yeah. Yeah, U bar is in this slide, you can think of just the boundary of U. So you just want to say that you have your open set, a space-time region, you put some boundary close of it, and it has to be inside another region. So there is a wiggle room between U and U prime. Now, you could think like, well, it's interesting because I have this net of relationships. What's the region associated with N? But notice that isotony is one way. I'm not saying that to every algebra, you have a corresponding region. To every region, you can assign an algebra, but to every algebra, you do not have necessarily a region. And so even though this corresponds to an algebra of a region, and this as well, and even though there is one other algebra in between, this does not correspond to any region. It can be completely delocalized. And in fact, it has to be the case from what we know from QFT, right? But the crucial aspect is that because it is the special algebra, it can be associated with a different Hilbert space. And by having that, you can combine Einstein separability, the fact that the algebras commute at space-like separated regions, with this property, and then you can approximately say that the algebra of your region of interest is basically the operators defined on the Hilbert space of this algebra that's in between the regions across everything else. And so suddenly you were able to separate your algebras as an algebra of a region and everything else. This is called the split property. And once you do that, then basically what you have, you can now write down uncorrelated states between U and complements of U. And if you do that, this is exactly what we needed before to define or to have statistical independence, and therefore having state preparation independence as well. So basically, you get approximately back the notion of subsystems, because now you can think of the region U approximately having a Hilbert space defined by the Hilbert space associated with the algebra, which is slightly enlarged than the algebra associated with U. Okay, so in principle, we are able to complete the table. And you see, like, we just have a bit more mathematical structure. And then we're done with the classical quantum mechanics, QFT. And you could be feeling very happy now, maybe. But we never really talked about the main type of QFTs that we care about. So the question is, well, what about gauge theories? And we actually do that for gauge theories because we're fairly abstract so far. So now let me give you an example of what happens if you have a gauge theory and what problem we have. And then we can think about those problems also in the point of gravity. So if I have a gauge theory, let's take an example, QED, for instance. You can write down the Lagrangian of a QED. You have the kinetic term for the gauge field. You have the gauge fixing term. We have the covariant derivative of the scalar field. And you have a math term for the scalar field. And then you know how to do gauge transformations. You can gauge transform your gauge field. You can gauge transform your scalar field. And then you have this notion of microcausality. So you have your scalar fields, space-like projected regions commuting. But we have a problem. Because those cannot be our observables. Because the scalar field is not gauge invariant. And so all this construction that we talked about so far about the algebra, so on and so forth, corresponding to things that we go and apply in the lab and measure in the lab, surely cannot correspond to something that is gauge. And so the task is, can we find other field-like operators that would be gauge invariant and still satisfy the whole structure that we defined before? And it turns out that you can. So you can find local gauge invariant observables in not only in QED, but generally in any Yang-Mills theory. And they correspond to what people usually refer to dress operators. Maybe you heard about it before, maybe not. But it's dressed in the sense that what you thought was a phi particle, which is a phi in terms of the phi theory, phi-free theory, that's not really the real particle. The real particle is a dress particle, which is going to be usually a combination of your phi field and your gauge field. And so in this case, for instance, one type of observable, that's just an example. You have a phi particle in one position, you have an anti-phi particle in another position, and they're connected by a field line given by the gauge field. So this is what people usually refer to a Wilson line. Those are just a lot of terms. The point is to say that you are able to write down a field-like operator, which is actually gauge invariant, but it's also microcausal. It's five of those relationships of commutativity. And so just to say that typically the things we talked about so far, they go through a normal Yang-Mills theories or the kind of theories that we have in our standard model particle physics. So to some extent, intuition goes a long way, right? We were talking a while ago, like 40 minutes ago, about independence of events. And then we are able to actually talk about independence of events in terms of measurements and states in many different levels. But of course, this is not really what we care about. Before I go about what we care about, do we have any questions about this? Okay. Yeah.
So what would go wrong in the scalar case with just doing the usual thing, which is with the Hilbert space and then taking boundary operators? Wouldn't these be gauge invariant?
They are not. They're not. Yeah. So they won't. They will be gauge invariant. They will actually the boundary operators are a type of dress operators as well.
Okay.
Yeah. So you can actually do dressing of. You can only focus on the boundary operator if you want. Typically, the problem is going to be that they are not going to be localizable as well. So if you want to talk about things in the bulk, then you actually have to be able to connect the boundary operators to things in the bulk. And then quite often what you do is like you shoot this Wilson line somehow from the boundary to the bulk.
Sorry, I didn't say, I mean bounded, not bounded.
Ah, bounded, sorry. No, yeah, no. Then they're not gauge invariant. No, they're not gauge invariant. That's the problem. Yeah. Okay, so what do we really care about, right? This is, and by the way, so I'm aware that it's almost an hour. So there are different options now, I suppose. I can talk a bit more about now how this goes with gravity, or we can have a discussion. And it's a bit, I'm very comfortable with whatever you guys prefer. There's been some questions as well, so I'm also take that into account with the time. So yeah, okay. Yeah. So what do we care about? I am, as Chris mentioned in the beginning, I actually am a cosmologist, even though I'm talking about all this kind of stuff. My PhD was in cosmology, and I was thinking a lot about the CMB back in my young days. And the CMB, as I'm sure everyone's familiar with CMB, so maybe I won't talk much about it. The main feature here is that it is this map of the sky that looks fairly thermalized. And we typically think that for things to be thermalized, they have to be interacting. So I have different subsystems bouncing around each other, and then they arrive at some thermal state. But for that, they have to be able to interact. And the problem with CMB is that we know that different patches of CMB, if you don't assume any fancy theory of their universe, they are causally separated from one another, right? And so this is basically what we had before. I look to the sky, and in fact, every other 2-degree separation in the sky is space-like separated if you go back all the way to the beginning of the universe. And so how come all those different patches of the sky seem to have more or less the same temperature and seem to be so homogeneous isotropic? And then we say, this is something I have to explain. I have to explain because, of course, I have those different patches of sky that correspond to different algebras, and they are commuting because they couldn't have actually interacted in the past. So is this true? Like, do we need to explain this or not? So this is one of the things I care about. Another thing I care about is about GAE experiments. I'm not sure how familiar you are with them, but nowadays there's a lot of discussion of people trying to probe the quantum nature of gravity by conducting experiments that aim to entangle two different masses in superpositions. And if this entanglement is only due to the gravitational interaction, they will take this to correspond to a somewhat proof that gravity has a quantum nature. Because at least for fine-dimensional quantum systems, we know that there is a theorem that you can only generate entanglement with local interactions if your interaction is quantum mechanical. Now, if you open up the very first papers that were written about this, so this is the drawings from Bose et al. Paper. Those are the formulas that they use to model the experiment. And there are a few things which are remarkable about the modeling of the experiment, is that if you look to their initial quantum states, which is right here, we have initial quantum states of mass 1 and 2, and this quantum state has very striking properties. So first of them is that it is a product state across each of those masses. But moreover, that the two masses are separated. There is a tensor product there. And so the question is, if I have a field theory which is gravitational, can I actually talk about subsystems, quantum mechanical subsystems, which are factorizable? And on top of that, I have ways of writing a product state for the initial state. So that's the kind of things that I care about. And in general, despite some level of contention, those are typical examples of what people call low energy quantum gravity phenomenology. So when people talk about cosmological perturbations, they are kind of one way or another quantizing both gravitational and geometrical degrees of and metric degrees of freedom, while the GAE experiments, they're tacitly being modeled in a way that you are basically having exchange of gravitons when you're entangling the two different masses, which is again corresponds to, in principle, a field being quantized. And the question is, once you have that, do you have the property of subsystem that we want to be able to talk about those things in a meaningful way? So the big question is, can we meaningfully talk about quantum systems that are gravitational, they're plural, and they're independent? Because we needed all of this structure to be able to talk about what happened at the beginning of the universe and talk about separate regions of sky, or when we think that we can probe the quantum nature of gravity in the lab. So I'm running out of time. I'm gonna give you some quick remarks about that. And then depending how the discussion go or not, I can show you the more formal aspects of what might go wrong. But I want to at least give you a feeling of what may go wrong when gravity is part of the picture. So when we do think about independent subsystems in quantum gravity, in particular in the context of low energy quantum gravity, what we're trying to do is to model low energy quantum gravity as a quantum field theory as well, as a spin-2 field theory, which is coupled with matter, typical degrees of freedom. And already in 2016, there was a remarkable paper by Donnelly and Giddings showing that in this context, typically that kind of dressing that we can do for other Young-Mills types of theory, that we can build observables which are gauge invariant but also local and satisfies microcausality relationships. That's not possible anymore when you try to do dressing with the spin-2 field, with gravity. So here we had gauge invariant observables that you can build and you can dress them. But in gravity, when you try to do that, you make operators become gauge invariant, but then they do not commute anymore at space-like separated regions. And that was a vital condition that we had together with the funnel property to prove statistical independence before. And Raju, a few years ago, 4 years ago, also put forward a big paper about the problem that you face when you have quantum gravity. And the idea here is quite simple. Basically, what you can have as a picture in your mind is that when we do quantum electrodynamics, I come here and I place a lot of electric charge in this room. And then you want to say, oh, if I put a lot of electric charge in this room, can I put whatever other charge in the other room? Or those two things are going to be actually codependent. And one way of doing that in quantum electrodynamics is that you put a Faraday cage around this room. So you bring a lot of other charges as you want, and you can isolate this whole room in an electric magnetic way, such that outside you can put whatever charge you want in a way that they do not interfere with one another. So we have this idea that you can do a state preparation in this room independently of a state preparation in the other room. Of course, with gravity, we cannot do that because you don't have basically negative masses or negative energy densities. In fact, you don't have negative Poincare charges. And that's kind of the intuition that you can grasp, that if I put a lot of mass in this room, I cannot go outside and put whatever I want independent of what's in this room, because there is gravitational flux coming out of this room that I cannot actually shield away. That's something that you can do for other interactions. And so this is something quite different for gravity. And when you think about these terms, if you remember from before, we proved that if I bring together isoseparability plus that funnel property that was a bit counterintuitive, we can show that these necessary sufficient conditions should prove statistical independence, which means that logically speaking, if I do not have statistical independence, then either I do not have isoseparability or I do not have the funnel property. And I just gave you this feeling that once you have a constraint, the Gauss constraint in gravity, which all the way back at the beginning of the talk is the constraint of the edge of the die between those two different corners. If you have a constraint, you do not have a way of preparing states independently across different space-time regions. And so you should perhaps expect violations of either isoseparability or violations of this funnel property. And to some extent, there is some mounting evidence that maybe what will fail in quantum gravity, while thought as low energy quantum gravity in field theory, is that we do not have anymore a well-defined sense of microcausality. And so maybe I'm gonna stop here. I'm already over time. I apologize for that. If you have questions, I can actually show more formally, or I can actually explicitly discuss with you at any point if you want. Also, I can make my slides accessible to you if you want, but I can actually show in the slides quite easily what happens when you do low energy quantum gravity. So you do the same kind of coupling that we did with QED with a scalar field, but we do that for gravity, and you show that you have an issue. And anyways, so I hope this gives you some intuition about some of the things that can break down when you do this more like bottom-up approach, where we start pushing what we know from field theory and algebraic field theory and the notion of subsystem independence. When you bring gravity together and you try to push it, those are the kind of things that start to become or to break loose eventually. This, of course, has a lot of implications to the notion of how do we even talk about subsystems. So last year, I wrote a paper in which I used all of that structure to undermine the way that we can talk meaningfully about quantum subsystems, and maybe even make a connection of that with the breakdown or the problem, the measurement problem, because the measurement problem is defined on top of having very well-defined quantum subsystems. And if you do not have them well-defined anymore, when you have gravity in the picture, perhaps you have some wiggle room to think about the measurement problem in a different way. But yeah, I will stop here. I'm happy to discuss as long as you guys want. Thanks so much.
I will have to give you a few minutes to teach them. I think there's a chance that the room is not occupied after this because we have to scan the video. So if we want to continue. The first question. No, let me take this one. Let me make a remark on that question. When I think about it, I will thank you very much. It's already a lot explained. I completely see what's going on. But I think at the end, when we arrive here thinking about subsystems case of probability, this is not surprising at all. How can it be otherwise? Why, on what basis should we expect that this will happen or what kind something to this capable? So yeah, for me, this is much more confirmation of what you should have thought anyway.
Yeah,
I
agree, but I think what's surprising is that the way that we model CMB physics, or the way that we justify that we need inflation, or the way that we are tacitly having back of our minds some modeling for GIE experiments, to some extent is not taking that into account. And I think that arguably is a problem, because perhaps we can, if this is true, if this follows, then maybe we should exploit this to understand better what might have happened in the early universe, or if we do detect entanglement in the lab when there are masses interacting superposition. As opposed to you not knowing this, saying that we have a problem, and then using the framework that is this framework to explain the problem away, which is really weird, right? Like you take low energy quantum gravity, and then you say, oh, the systems are independent, so they didn't interact. So now I need to explain what happened in the early universe for them to interact. But the very assumption of the framework that's being used to model inflation, for instance, is a framework that's telling you that maybe you shouldn't trust the fact that the systems haven't interacted. And that's puzzling to me. Yeah.
Oh, sure. Thank you. Thank you.
Yeah.
Let me first make sense of what I'm thinking about. So what I'm thinking about here is basically how
So we've seen a bunch of results where we see, especially against the gravity case, the bunch of expected independent properties that they basically are on the scale of variation of these properties. I was kind of curious how much of these should be brought back to a failure of this independent condition, and how much of these can just be brought back to the fact that, in some sense, when we use the gravitational theory, the available regions which are suitable for identifying the systems are a lot less than we expect. Because we some extent we're already doing this in game of quantum field theory. Because there are regions where the quantum field theory is by I mean, you mentioned the various property like there is simple example to take like wedge the wedge. So already there we are saying, well, if we think that the speed property, or anyways, yeah, this is the property defines what it means for something to be an independent subsystem, or that the quantum field theory you are going out to say, well, wedges are two wedges cannot define independent subsystem. And to some extent, I remind now, and like the details that there is a guy in my paper exactly where he tries to show that if you look at like extremal regions, for example, in gravitational theory, then you do get exactly what you're saying doesn't happen, because the basically the masses on both sides, or like quantum invariance on both sides of the extremal region, one is going to be positive and one is going to look negative. It's not it's going to be active. So it's going to look negative. And I can pass.
Yeah.
So like I was just wondering, unfortunately, it's not really clear for us. But to some extent, I'm wondering how much of this is really a failure of property, and how much of this is just the fact that we just need to completely rethink which regions are suitable to localize localization regions for subsystems in this theory.
I'm not sure what to reply. Because I think what you're pointing out is like, well, maybe the whole approach is mistaken somehow. That somehow we should think about what are proper regions of space-time where we do physics. These are not the kind of like regions I have here.
Yeah.
Like we should rethink the whole thing from scratch.
Yeah.
And I welcome that. I think we should do that. I think someone should do that. Maybe I won't do it, but someone should maybe do it. So the more conservative take from this talk is almost a criticism to the way that we've been using low energy quantum gravity, which is the kind of answer I was giving to Chris just now, and talking about the way that we justify inflation for the early universe, or the whole discussion about, oh yeah, if we detect entanglement in GAE experiments, gravity is quantum. Well, wait a second, what's the grounding for those claims? But to your question, I completely agree. It's like, so if you talk to someone like Carlo Rovelli, he's gonna say like, this is all like, it's a very nice math, but clearly I'm in a space-time region and you're in a space-time region, and there are very well defined, strong sense of independence that we can talk about. And so we should somehow adapt the physics, the gravitational physics, quantum mechanical or not, to correspond to that sense of independence that we have when I go to the lab, right? I mean, we do every day, we do many experiments across the world, entanglement or not, quantum mechanical or not, and we have countless tables of data, and we don't expect that everything is correlated in weird ways. And maybe it is, but to the degree of approximation that we're working at the moment, we don't see that. We really think that I go to the CERN and I make an experiment here, I go to SLAC and I make an experiment there, and we don't expect those things to be completely correlated because there is some ill-defined sense of independence coming from quantum gravity. And so you could take that as a hint that maybe this is not the best approach. But then what is the approach? I don't know. People, I would assume. Well, this was, so I'm actually familiar with the paper that we're talking about. I saw the talk, I forgot his name, yes, Norwegian guy. Yeah, exactly. But the problem with that is that it's not a background independent claim. So yeah, that paper, he's taking a particular background, because you need to have the trapped surfaces or extremal surfaces, and it's a classical result. So to which extent you can generalize that to the quantum case and make it background independent, I don't know.
It seems to me that maybe, or let me say it that way, it's not obvious that this points to some problem with the equation itself. Maybe it just means that we don't understand what it means to make like low energy approximations in the right way, because clearly that's what we will need to get to the conclusion that CERN and slack or a reasonably good approximation because independent approximation. But anyway, I need to go to that for So how do you have to go where there will be possible
Thanks, I was interested in the, I mean, all was interesting, but what caught my attention was another part when you said that I have to really almost problem in the context of and of course, if you cannot, separate subsystems, then how does the flux happen and how are we going to, so we go into a flux so how do you formulate the manual problem?
I wouldn't reformulate it necessarily. I mean, I would still have the same formulation. That the very naive thing I would say is like you do have something like a collapse going on, and the question is understanding what we mean by collapse if your notion of subsystem is not actually fixed and invariant. And so, and in that context, then you have much more room to talk about those things, because suddenly it might be that your final state, it doesn't correspond to the same system that you had before making the measurement. And then there is no notion of collapse happening whatsoever. It's just that those are not the same systems anymore. But then I have to qualify what I mean by that, because then there is a notion of classical system, like my phone remains my phone when I hold it or not. I'm making quantum measurements here, right? So the classical system as my phone remains the same. Clearly, there is a sense of persistence, or not sure if that's the best word, but there's a sense of invariance of this physical system in phase space. But it could be that the corresponding assignment of a Hilbert space of my phone on the bigger Hilbert space of the whole universe is not something which is fixed over time. And so when I see my phone over and over again on a single state, it could be that it's a single state, but not on the same Hilbert space that I had before actually making the observation. I'm being very vague, because actually you have to, so you can be more precise if you want. We saw that in this talk, we did a lot of work to arrive at the fact that we have a way of breaking down the Hilbert space into factors, having a tensor product structure. It wasn't something that was a God-given, right? And one of the crucial assumptions we had at the beginning, when I told you that there was this if and only if relationship between commutativity of observables and Hilbert space being factorizable. Now, if I don't have this commutativity anymore, then I don't have anymore the sense in which I can always break down my Hilbert space. And so breaking the Hilbert space would become something which is approximately true, but wouldn't be preserved in general. And so the analogy to think about this is actually to think about GR. Forget quantum mechanics. What happened between special relativity and GR? What's the jump? You can think of GR as basically special relativity in a point-wise sense. At every point, I define an orthonormal coordinate frame, my tetrad system. And if I was in special relativity, once I find that system, I can just stick with it. Of course, there are many tetrad systems for the different inertial observers. But once I am an inertial observer, I can define a tetrad system, and I can just stick with it. What happens in GR when you have curvature is that you have to keep updating your tetrad system as you move along your geodesics, or as you are around any curved spacetime. And what's your tetrad system? It's basically a way of taking your four-dimensional space-time and breaking into four orthogonal unit vectors, if you want. So you thought that here that's what we do, right? I break into between X, Y, and Z, and I can just move around with my rulers and I can go and measure everything, and I don't care about that. If I was in space-time, I wouldn't be able to do that without updating constantly how my rulers play with one another. Which is another way of saying that also the factorization of space-time dimensions in GR is not fixed. It has to be updated as you move around your manifold. So I'm saying that something similar will happen in quantum mechanics. You break down your Hilbert space, but that factorization of the Hilbert space shouldn't be thought of as fixed anymore. And then once you do that, then you have a whole different sort of question you can ask and an approach maybe to address a measurement problem.
And the question of implication of GIE. So we can model GIE with a two-finite system. Okay, and then assume that we need some more continuous. You would think this kind of subsystem, something like a ZVT, which you can model still with encoding potential, with two systems, and should also continue to be true if you move a bit further up in energy scale description, right? So while I agree that at some point there's a good reason to question applications of subsystem split-ups and you bring invariant. Maybe you could say it's a GIE case, a regime, but you can always describe without using let's say even field theory, which then however for pedagogical purposes put into the framework of that. And then you could however say, given that you can only describe it as a knowledge description, but still holds. It's very likely that this should also then hold still even if I change the description, right? I mean, I guess there's something different between saying in general the gets broken and considering relevant for the GIA, because it's more like a worry, right? Which one would probably fill out more and I would find yes or no, so much I can factorize, I cannot factorize. Yeah. Right. So good. So I agree with you. I think the problem is that people want to make the GIA description local. And then when you're doing local, then you are actually thinking about quantizing the spin 2 field. And then you have the gauge issue. And then you are in the regime in which you should do better in terms of talking about subsystems or not. Especially if you want to then go as far as to say that, we're probing space-times being superimposed. Yeah, in a way, I agree. The way let's say you start with bottom up, right? If you just do subsystems, so the two parts of the brackets, then the moment action not with this system yet. Okay. And in this regime, you expect something to happen about it. Now let's use some more formal language to speak. There's still this basic physical idea of that there are these two independent systems doesn't get demolished by that I use some kind of more advanced formalism, right? So I would think the factorization, at least for the two brackets, I'm not sure really about the rotation view, I have to be honest. That should still somehow stand the test, even if I use this other formalism. It's just that, so to speak, there might be some error. Sure. Right? You would agree with this more? No, I basically, as I was saying before, when I talk about CERN and Slack, whatever is happening, it seems to be that we are factorizing it in some way or another. So of course, effectively, this is the case. I think I take problem with we take this effectiveness of the physical system being factorized to be mathematically represented as factorized. Physical systems are independent. We represent them as factorized,
But then within the formalism, we extend the formalism to a regime in which that doesn't hold anymore.
Maybe, yeah.
But still we want to go to this regime to conclude things at this level. And that I take problem with.
Very when they have to split up, you know, by one side to the G. I think if they just never say that only meant to model the specific vector specifically, that it's probably okay. You just have to think of the speculation that somehow be rigorous.
Which I think that's fine, but then again, they want to conclude more than that. I think that's the problem. That's like where I don't go along with.
If they just mean bracket that they are going to build them maybe in 10, 20 years, maybe then they don't keep on there, but I guess they're right. The theory is probably that we should do more about the field keeping energies out, right?
Exactly.
That's weird.
I think that's weird, yeah.
So the way it undermines looks good.
Thanks. I have a conceptual question concerning discussion in subsystems, and especially related to the independence. So just going back to what we had earlier, then if you have two entangled rectangles, if you look at the control system, I mean, these are no longer independent. In this case, you don't have independent systems, right? There's just one system here.
Well, yeah. Well,
Yes.
no, you do. Because again, it's a bit tricky. I know a lot of the definitions, but it's one way, not the other. Which means like you have electron 1, electron 2, and then you have a state of electron 1 and state of electron 2. And then for them to be independent, you say there is I states in the whole system that reduces to the state of each of those. But it doesn't say that you cannot have global states which do not reduce. So you, of course, an entangled state is going to be a state that's going to have correlation. But the systems themselves remain independent given this definition. Just because you can talk about the state and observable of each system independently. Yeah. Okay. Now, just to maybe complement or complement the answer, that's exactly what doesn't happen in QFT, at least naively. Because there, what happens is that all the states are entangled. And then you never have a product state. And that's the same as saying that there is no notion of states independence preparation. Then you have to work harder and have these kind of properties that we discussed here. Yeah. But if you had, so in another way of saying, if I gave you two different systems, but every possible state of those systems are entangled, so you only have global states which cannot actually be ever seen as independent. And then you don't have the uncorrelated states. You still have statistical independence in the first sense, that you can reduce each state for each system, but you don't have in the product sense that their statistics are independent from one another. So it's a bit of a subtlety, but yeah.
Yeah, so I'm still working on my understanding of the different sense. So for me, we're going to integrate there is standards. But I'm trying to understand what the discussion about the inequality that evidence is used as a name of one of the premises, like independence in measurement settings, so you can independently prepare different.
Right. So I guess connecting with Maria's question is the second, now thinking back about your question in the talk, is the second sense which is there. So not only, of course, can have the independence of the states of each of them, but you can prepare the whole thing in a product state if you want. It can be completely independent.
So you accept independence and you already...
No, I accept. Yeah.
But here, when we say not statistical independent,
Yeah.
uh,
So again, so I know it's a bit confusing, and I keep confusing myself over time, over and over again. It should take this statement to be a statement about the algebra of those different systems, not a statement about a particular state of the system. So you can have a system which can be decomposed in subsystems, and they can have an entangled state. That is not a problem for statistical independence whatsoever. Yeah. So not having statistical independence is actually something much, much more severe, because the Bell Live experiments, they do assume that you have statistical independence.
yeah, okay, so I get you right. I already denying statistical independence of general set.
Yes.
Because, so here is why I understand that, because this is not surprising. But I think if that's the case, that's pretty surprising because we're going in the superdeterministic direction, which is more
Yeah.
or the unity working, okay, let's apply inequality, we get homogeniity, but we also
Yeah.
So it's more defined that there is independence,
Yeah.
and the far more radical than just
Yeah.
getting rid of non-necessary. But I think people don't really. I mean, I don't know if you look at the literature on whether it's fine to reject independence. Because there are many weird issues popping up.
Yeah.
Really blended independence, like
Yeah.
because the way you define isolated systems,
Yeah.
systems, the very concept of the real experiments,
Sure.
just in the logically,
Yeah.
logically separated. But if you start really messing this up,
Yeah.
a bit like one of those you open, like how are you going to trust?
Yeah.
When you do it in the lab.
Yeah.
Okay, so what do you think of that?
Again, like so I don't want to be normative of either way. I think this is more to point out that if you are in this regime of low energy quantum gravity, you might be facing this kind of issue. Now, the question is this what the world is about or not? Because if the world is not about not having statistical independence, then the question is like, well, what's the theory then in which that's preserved? With a bit what Chris said as well, it could just be that our approximation scheme to go from proper non-perturbative quantum gravity to low energy quantum gravity is not what we do typically, of just linearizing acid equations and quantizing spin to field and whatever. Maybe that's not the procedure if we end up here. Now, I want to be open-minded. It could be, I don't know, like the world is weird. It could be that the world is actually not statistically independent. I don't know. So, like if you do not have statistical independence, then maybe things like the C and B being thermalized, they're obvious. They're not a problem. And so in the end, it's going to be like, to which extent your theory is empirically adequate and how well it explains the phenomena in the world. And then that's going to be up to future and many future generations, I suppose. But I don't have, so back to your initial comments, I haven't really read much into the literature of like, if I evaluate this, what kind of problems do I have? And so maybe I just have too many problems that I really do not play with this. And then I take this as a principle to say, okay, this approximation scheme is not really working for me. I don't know.
I mean, just in one problem or meeting with independence, you might get a frame of empirical clearance, in the sense that the results you build were created from accepting statistical independence in the process, and build your data, used to let people come from the start.
Yeah.
Undermine principle.
Yeah.
So you'll be like, okay, so thinking maybe we should let go of principles that we're trusting into the result. So there might be not a kind of similarity with and there is discussion.
But then I can also be provocative, and I can say the following. Maybe when people were talking about like, oh, maybe notion of simultaneity is not true anymore. I don't know actually exactly how disturbing that was at the time. because I guess people were relying a lot on the idea that, of course, we can meaningfully talk about simultaneity across different observers. And then it turns out that simultaneity is violated, but in our Earth-like scales, pretty much completely neglected, like negligible, like it doesn't affect us, right? And so there could be exactly.
But then there is a problem of, yeah, I mean,
So there could be a sense in which this violation is really something about we're getting Planck-like corrections at very high energy level, that this thing doesn't hold true, and it's affecting just like large scale kind of observations. Like yesterday, we had a whole talk about fine tuning, right? It could as well be that, of course, things are actually not fine tuned because just that there is a sense in which everything is more connected than we had expected.
I mean, I would say the level
Yeah, yeah,
of
sure.
who wants to read that or maybe who wants to question? Right.
Yeah, thank you.